Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Most importantly, bom dia, Brazil. Welcome, Florianópolis. Today, our speaker is NATÁ Machado, and he will tell us everything and more about the classification of saturated felt bundles, the discrete case, and beyond. So please boldly go where no one has gone before. It's all yours. Take it away.
Okay. Thank you, Piotr. Thanks, the audience. Um, it's a great pleasure to be here talking to you. I'd like to say that this is a joint work with Stefan Wagner, who is in the audience. And also, this work started at IMPA, in,
Haha.
in the working in the quantum symmetries workshop. So it's a big pleasure to be here talking to you about it since you allowed us to go to visit IMPA. Okay. The date is wrong, as Piotr warned me. Oh, but I'll fix it later. Okay. So today I'm going to talk about classification of saturated felt bundles in terms of an invariant that I'll present later, right? But the outline of the talk is I'll start with an introduction. Later I'll talk about Banach bundles, and then specify to felt bundles, and then classification. Here we use some cohomology theory. So starting with an introduction, motivating bundles and stuff. Uh, Everyone knows, let G be a group, for instance, and let A be an algebra. We say that an algebra is G-graded if there's a family of subspaces in such that the multiplication of this let's say fibers, these subspaces, satisfy this condition here. So if you have an element in AG and another one in AH, then if you multiply them, you go to HEH. Okay. And another condition, we ask that this direct sum here, that the entire algebra is the direct sum of this closed of this subspace. So closed. We'll talk about topology later. And in this case, we say that the subspace related with the unit of the group, okay, that's EG, we call it the principal component. Okay? So to every, we say that this is a grading. So to every grading, we have a, let's say, a degree map or a projection. What's a degree map? Let me take a ticker pen. So we have the degree map here, where you assign to each element in AG G. Okay, so you go here, you remove 0. Okay, and then you can assign X to G if X belongs to AG. I'm sorry if the pen is so bad. That's because of the software. It shouldn't be this way. Okay, that's what we call a graded algebra. Good example are the Laurent polynomials or Laurent series, right? That are polynomials on in Z minus one. Okay. Let's say Zn and Z. Okay, where An belongs to complex numbers, the Laurent polynomials, and the sub the comp the homogeneous the sorry these subspaces, the An subspaces are the complex numbers times the nth power of the variables. Okay. That's the Laurent polynomials. Okay. Cool. Why are grading important? Important. Well, they simplify computations. Sometimes it's easier to analyze each of these components instead of the algebra and prove properties about these guys over here. Okay. Uh, Another thing is sometimes you can identify substructures inside the grading. and try to understand what happens in the whole algebra. Okay, and also you can study permanence properties. That is, properties that happen in the principal component or in the unit fiber component. Let's call these guys fibers. We'll say it later, but let's call this fiber over G, and the principal component is the unit fiber. So sometimes you can study what properties the whole algebra has. Sometimes you can study properties of the unit fiber and then to try to understand if it goes to the whole algebra. So you can also establish new connections using cohomology, as we will see later. A good example is the Levy path algebras, that if you have like a graph, you start with a graph, and then you build the Levy path algebra that is the following. So you start with the generator set, the vertex and the edges, and also what we call here the ghost arrows. So let me try to draw what the meaning of these things. So we have a graph. I'll just draw one arrow here. Yeah. And when you're going to build the algebra, you also consider another set of arrows that we call the ghost arrow. They may not exist, but you have to understand that they work like this. Okay. And then your algebra based on this graph is has this set of this set as generator, and it's subjected to this relations. Okay, so whenever you have two vertices, let me write here V. Whenever you have two vertices, you can multiply them. The multiplication is non-zero if and only if they are the same. Otherwise, it's zero. Okay. When you're multiplying the source of a map, here, let me just the source everyone knows, but it starts on the source and it ends in the range. Okay. Whenever you multiply an arrow, an edge, or an arrow, yeah, an edge by its source on the left, it's the same as having the arrow. And whenever you multiply it, an edge by its range on the right, you have this. And if you understand that these F star arrows comes from building this ghost arrow in the opposite way, like if you have F here, and then you build another one starting on the end of F and finishing in the beginning of F, then it will make sense. If we are like just standing this property. Okay. And another interesting relation is that whenever you multiply two arrows, a ghost arrow, whenever you multiply a ghost arrow by another, by a really an arrow in the graph, so it will be non-zero if and only if they are the same. And if they are the same, you're going to get the range. It's like you're doing like this. You're coming from the range of F to the source of F via F star. Okay. And then you plug F here, you continue, plug F here, and of course you end up with this. So these are the relations that are involved in building this the Levy path. The interesting thing is it's a graded algebra. Okay, so we will say that the degree of an arrow is 1. The fiber of 1 is a graded algebra, over Z. That's important to say. So we need A1. What is A1? Is the span of all the symbols F, A1. Here we could write delta F, but I don't wanna mix it with this delta here. That's Kronecker delta. But I'll understand. I think you guys will understand delta F A1. Okay. and A minus 1 is delta F star, where F star is a ghost arrow. What's a ghost arrow? Is a copy of the set of arrows, but with one star above it. Okay. And then if you multiply these two subsets, we need to get, since we are dealing with a grading, we will get to where? To the delta F star, but we already know what is it. It has to be a vertex in the graph. So as it's already written, we have A0 is equals to delta V, span delta V. So
Wait, but that's not everything.
Yes, we have the other. You mean the other gradings, the other spaces?
No, but A0 is not just the span of vertices. I mean, you take anything like alpha alpha star, it also will be in the degree zero.
No, but the relation will impose this, right? The
No,
relation will get.
I'm not. No, 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 no. I'm saying alpha alpha star, not alpha star alpha. You don't take a sum.
But
You might have an infinite emitter. So
no,
if you
but
take anything of a
no,
form,
but
if you take anything of a form alpha alpha star,
mm-hmm. And
where
some.
alpha is any path, when this is in degree zero,
Okay,
and it's not a vertex in general.
no,
Also
but
in
I'm thinking. I'm
higher
thinking.
degrees, if you want to have degree one, in general you write symbols of the form alpha alpha star because this is how linear basis is constructed, and you take
Mm-hmm,
so you take in general you have alpha beta star,
mm-hmm.
and you take the difference
Yeah.
of the lengths of a path, and this is your degree,
Okay,
and
okay,
then you
okay,
take the
okay.
span. This then you have everything. That's just
No,
wrong.
okay, okay. Yeah, you were right. You were right. You're right. That's a
Okay,
mistake.
but let me ask you the following question because we're discussing it
Mm-hmm.
today for quite a long time. So you see, this assignment of ghost edges to edges and vertices to vertices by identity. It defines for you a canonical star structure, a canonical involution on your Leavitt path algebra. Okay?
Okay. Mm-hmm.
Now, we asked ourselves today the following question. Imagine that you have two Leavitt path algebras, say LKE
Mm-hmm.
and LKF,
Mm-hmm.
and even you can assume that they are unitals, so they have finitely many vertices. And imagine that you have a unital algebra homomorphism. Does it have to preserve a
Okay.
star structure?
Um, I'm not sure if that's enough.
No, it does not.
Okay,
You
okay.
can
You're
write, but it takes a while to get a counterexample.
okay. Okay.
So it is not true, even if it's a unital algebra homomorphism, it does
Mm,
not have to preserve a star structure.
okay.
However, if our arguments are correct, we were doing it over dinner, so one has to double check it. But if you assume that you map vertex projections to projections, I mean self-adjoint
Mm-hmm.
idempotent, then you can prove it preserves the star structure. But it's
Yeah, okay.
quite a lengthy argument.
Okay. No, I was sure that there was an assumption that should be made that it will happen. In some sense, I understand it. There's even a result in concerning operators where if you have like a generalized inverse, when this generalized inverse, this Penrose inverse, I'm sorry, is the adjoint. So it's
Uh-huh.
for me it sounds like similar things, and it also has to do with some projections.
Well, okay, maybe. If I remember correctly, in Murphy's book, there is a proof that if you have an algebra homomorphism from a sister algebra to complex numbers, it has to preserve a star structure. I think there is
Okay.
such a result in Murphy's book. And in general, for sister algebras, it's completely easy to write down an algebra homomorphism which is not star preserving, you know, take Teplitz algebra and so on. But then when you want to go to these nitty-gritty details of, you know, all these
Sorry, I'm not
relations which are
hearing you,
plentiful
Piotr.
over
I hope it's
here,
not my.
so relations have to be
Okay.
satisfied by the star has to be violated. Then it turned out to be quite involved. But yes, it is not true. It is not true. However, I'm still impressed that it suffices to demand it that you preserve it on vertices. So it's like a very small portion, like the commutative part of your algebra, you know.
Mhm.
If they are, you know, disjoint. Anyway, so just on this very small portion, you demand that you preserve the star structure, and that's it. It's preserved globally, and no assumptions in the graph, any graph.
Okay. Later on, I'll talk to you in private about a similar result that I have used in my thesis. So.
Sorry for interrupting your talk, but I wanted to mention it.
No, no. By the way, so for instance,
How many?
using the Levitt path algebra, if you consider this the simplest graph ever, one arrow and one edge, one cycle, then you have the Levitt path algebra of this graph is the Lohan polynomials that we mentioned before. So let's go to graded C-star algebras. Now we have norms, we have topology, and then we will say that a C-star algebra is G-graded by a discrete group, if there's again a family of subspaces, but now we are asking them to be closed. Okay, in such a way, when you multiply HE to AH, you're going to get to HEH. Okay, for all pairs. Now we have involution, so we have to ask something about involution. We ask that when you involute AG, you're going to get to AG minus 1, and the sum, direct sum over G of this closed subspaces is not the whole algebra, but it's enough to ask that it's dense. Okay, so we ask that's what we call a G-graded algebra. To ask this to be the whole algebra, it would be too hard, too strong. That's also if you are summing up to infinite things, it will not happen. Okay, so where this example of such algebras appear, if you have a continuous, strong continuous action of a compact abelian group on a unit of C-star algebra, then you have a grading by its dual group. So we know that if G is compact and abelian, then G is compact and abelian, then this group, the dual group, is discrete. Okay. And let's say that's a C-star. Let's so assume that G acts on a C-star algebra A via automorphisms, acts on A. Okay. So we can prove that the dual group defines some closed subspaces that we call spectral subspaces, right? So this is not an X. This pen should be working better. I'm sorry. So that's chi, a chi. You define for every character here in the dual group a chi, and it consists of the elements of A, where when you apply the action to A, you're going to get chi G times A. And it happens not only for one G, it happens for all G in G.
Sorry, Nata, correct me if I'm wrong, but here you can just write equality, right?
Where?
Here.
Yes, it's equality, but it's enough
Okay. Yeah.
because you
It
apply
follows.
again. I
Yes.
think,
Yes.
yeah, yes. That's the weaker assumption you need
Sure.
to
Sure.
be agree. So we call these guys spectral spaces. No, sorry guys, I missed the word here. Spectral subspaces maybe, but it's this equation resembles eigenvalues, right? So I think these guys are called spectral subspaces. So these guys, when you sum them up, you sum them over the dual group, that's a dense space in the whole algebra. That's a result by Levin-Pontiac. Okay. So now we specify the fact that I've mentioned. Now let's specify to C of t, continuous functions on the circle. Okay. What can we say about this C of t? Let's see where's the grading here. Okay. So let's start with an action of the circle on C of t, an automorphism action, where whenever you have an element in the circle, okay, alpha w of f of a function of the circle will act like this. So you multiply z, you like rotate z by w, let's say in this way, and then we apply f. Okay? So that defines we can prove that it defines a continuous action on C of t, and therefore, because of the previous result, since the dual group of t is z is the integer number, we have that C of t is graded by z. Okay. That's a gradient of these guys. Let me just mention the one thing here is that, of course, it's an identification, but we have this chi n here and in z, where chi n of z is z to the n. That's how z is the dual of it. So viewing this way, we have this homogeneous, the spectral subspaces, CTN. Like here, I'm using parentheses, but you have to interpret like C of Tn. Okay. And we can prove that these guys are also multiples of one single function, okay, Fn, that this is what we call the Fourier mode. If someone wants, I can prove it. I can show it. There's it. Okay. So every homogeneous space is C, right? And then the algebraic direct sum forms a dense subalgebra. That's the result that we mentioned in the previous. It means that every function can be approximated by its Fourier. Okay, now let's talk about Fell bundles a bit. It shouldn't be Fell bundles right now. Okay. Sorry, this. We'll talk later about Fell bundles, so I will not. It's used in. It's a generalization of graded sister algebras here. We'll see that whenever you have a grading, you have a family of spaces, and the degree map introduces like a union of closed subspace, and you have a bundle. Okay. These guys you appeared in several areas like physics, and they are studying in sister dynamical systems and B-module theory, for instance. So for us, all Banach bundle or all topological spaces from now on will assume to be Hausdorff. Okay. And whenever you have a map like this, a surjection like this, we will define B of X like the inverse image of one singleton, the singleton X, okay? The fiber over X. Well, so let's talk about Banach bundles. Okay, a Banach bundle, it's the drawing a picture is better. So you have a base space X, and attached to every point of X, you have a Banach space. Of course, there's some topology here connecting these things, but that's the way I think it, the way I draw it. Okay. So you have a Banach bundle. It's a triple where B is a topological space. Okay, it's called the total space. X is a locally compact space, and pi is a continuous open surjection. So we usually denote this. Okay. And in such a way that every inverse image of a singleton is a Banach space. Okay. And also the following conditions are satisfied. For this setting to be a Banach bundle, we have some conditions. We ask some conditions that are these ones. We ask that the norm, this function that takes one S in B and calculates its norm, is continuous. Observe that here we have several different norms taking place, because to each fiber we have a different Banach space, and therefore we have different norms. So we should, in fact, say put an X here and saying that if S belongs to Bx. But we assume everyone understands this abuse of notation. Also, besides asking B1, we ask that whenever you can sum pairs of elements, that is, whenever they are in the same fiber, then the sum function is continuous. Also, we ask that the scalar multiplication is continuous for every lambda in C. Multiplying by lambda is a continuous function on B. Okay. Again, here we have different actions of C in each Banach space. And also this before condition here that says the following. If you have SE, a net of elements in B, in the total space, and in such a way that the norm of SE converges to 0, and when you project it down, when you see it in the space, the base space, it's the image of this sequence under in the base space converges to some X, then the sequence in the total space converges to 0 in the fiber X of this guy here that SI is converging. Okay. This condition appears to be kind of hard, or hard is not the word, but what's the sorry, I miss the word here, but it's strange, let's say. But this condition, for instance, allows us to guarantee that the topology of B, when restricted to Bx, is exactly the norm topology.
I think there are two questions.
Okay.
First, if I could ask a question, so is there any condition in the spirit of local triviality?
No, it will be mentioned later. Yeah, okay. But in Banach bundles, we have Banach bundles in infinite dimension that they are not locally trivial. Okay.
They are not.
So far we have, yeah, they are not locally trivial. Yeah.
Okay. Okay, thank you.
Thomas?
Okay, so I have some doubt in the point number 2, B2. Look, you have this Cartesian product. Shouldn't it be fiber product over X?
Yeah. Cartesian. So maybe it's.
Okay.
So
okay.
Go.
Okay.
Yeah.
Okay.
Cartesian, it's not only the guys that it's not the whole Cartesian product. The set is defined for the guys that are in the same fiber. Okay, this condition here. Okay. If it happens they are in the same fiber, since this fiber is a Banach space, we can sum them. Okay. Right?
Okay. Yes, okay. Yes.
So what I was talking is that this condition for this B4, for instance, guarantees for us that the restricted topology of B to Bx is the same topology as the norm topology that Bx has. Otherwise, it could be weaker. Okay, it's not necessarily the restricted, not necessarily the norm topology. It also guarantees that the zero section is continuous. So, for instance, a trivial example of a Banach bundle is a trivial bundle. So assume you have a locally compact space X, the base space, and then you have a single Banach, a unique Banach space B, and then you consider the Cartesian product XB. So we are attaching to every point of X fiber, the same fiber. Okay, so that's a Banach bundle. I guess we have a. Oh, that was mentioned. Okay, so that's what Adam, sorry, I think it's Adam. Adam asked. Not all Banach bundles are locally trivial. Okay. Condition 4, in locally trivial bundles, condition 4 is always satisfied, that condition on the sequences. And here another point is that if the fibers are all of finite dimension, it's locally trivial.
Sorry, can you show again condition 4? I just don't remember your enumeration.
The
okay,
sequence
before.
one.
If Si is any net of elements, so this is about the topology. Okay.
Yes, exactly. Okay. So
I have one more.
Please.
In this fourth condition, you formulated it in terms of nets. So this suggests that this topology on B, this calligraphic B, need not come from a metric. Is it true?
That's a good question. I believe it doesn't need to come from a metric. It's not. Okay. I'm not sure if they prove that all Banach spaces are metrizable.
Okay.
All the Banach bundles. Sorry. I'm not sure.
Probably the space X.
X cannot be metrizable. Even not every compact Hausdorff space is metrizable. So.
Okay. So
no, but X is not compact. Locally compact.
Yeah, but even if it were compact, it still wouldn't be metrizable necessarily.
Okay.
So probably the space, this underlying space X is somehow responsible.
Exactly. Yes.
Non-metrizability. Okay. Thank you.
Okay. I thank you. So one thing that we could think, when you imagine you have a discrete space X, or a set, you have only a set. Okay. So if you have a family of Banach spaces, for every point of X, if you have a family of Banach spaces, Bx, so the disjoint union Bx is a Banach bundle. Okay, because the conditions, when you don't have topology here, these conditions are like kind of vacuums. Okay. But now, suppose you put here topology. It was a set. You have a family of Banach space for each X, and that's a Banach bundle. Okay. But somehow you come up with a topology for X, and then the question is it possible to build a topology on this total space here in such a way now we have a Banach bundle considering the topology on X, this new topology on X? And yes. There's a Doran and Fell proved the result about it, and you need to talk about sections in such a if you want to topologize this B here. Also, let me just say that it's common to say that B if you have a set discrete topological space, this guy is called untopologized. Okay? A non-topologized bundle comes in this sense when you're like forgetting the topology of the base. So this is proved by Fell, Doran also. Okay, and that's the result. If you have B and you have a surjection onto a locally compact space, just a surjection, such that you have the fibers are Banach spaces, and if you want to topologize B, if you have a complex subspace, a complex linear space of sections to this pi here, okay, in such a way that every fiber is fulfilled by this gamma, the set of sections, in this sense that whenever, if you fix some x and apply all sections of your set in this x, if you get a dense subset of this of the fiber for if it happens for every x, and also if you have this continuity map here, okay, and again for every section, you fix a section and analyze this continuity condition here. If it happens for every f, then Fell proved that there exists a unique topology. You can topologize the bundle. There exists a unique topology on B that makes this triple a Banach bundle. Okay? And also the set of sections you started with is you become continuous. Oh, let me just say that this notation here stands for continuous sections. Okay, at the bottom. So whenever you want to topologize a bundle, you need sections. Okay, let's talk about Fell bundle right now. Now
again, two questions.
Tell me.
Okay, if I can, could you come back to the previous page? Yes. What about the continuity of this surjection?
This one?
Mm-hmm.
So you have this set theoretical map phi. Now you are topologizing. Now you are topologizing this by this
yes,
dense subset of sections. Okay.
And
then you can identify this subspace gamma with as a identified with the subspace of sections. But what about continuity of pi?
No, pi will be a continuous open surjection. Is there a unique topology that makes that's in the definition of Banach bundle? Pi has to be continuous and open.
Okay.
So that's that's the thing. That's the thing. If you have this set of sections, a previously defined set of sections, you find a topology in which these sections, the previous set, will be continuous and turn this guy into a Banach bundle. Okay. That's the result. You come up with a topology that makes this continuous open surjection. Stefan?
I just wanted to mention that. I mean, I remember when we were at IMPA, so that was the tricky part, and we wanted to construct these Fell bundles. So the idea was, of course, you take the topology of the group and the topology of the unit fiber, and then we looked if there's something canonical, but it turns out there's not. And what you really have to do to topologize this is to use this lemma. So, I mean, of course, if everything is discrete and so on, then you don't care. But the way to get a topology is really this lemma by Fell. Yeah, so topology is not that easy in that sense.
Okay, thank you, Stefan. So now let's talk about Fell bundles. We defined what is a Banach bundle. That's let's think of a family of a union of Banach spaces. In such a way, you have a projection, okay, over a group. But now we want more. Here we have in a Banach bundle, we have what? In each of these lines, we have sum and multiplication by scale. But right now we want to somehow relate fibers with fibers via a multiplication. We want to multiply elements of different fibers. Okay, that's something that resembles two gradients. Okay. So what is a Fell bundle? A Fell bundle is a Banach bundle. We start with a Banach bundle over a locally compact group. Okay, we fix the identity of the group to be, and there's a multiplication map in the total space. Okay, and also an involution. Okay, and what are the conditions that this map satisfies? First of all, when you multiply an element of the fiber BG with an element of the fiber BH, we're going to get to an element of the fiber BG of BGH. Okay. We have also this norm condition. Here we have three different norms, right? Whenever you have an element S in BG, well, you have T in BH. Remember, you're going to get ST in BG of H. So the multiplication satisfies this condition. Okay. The norm in BGH, the norm in BGH of ST is less or equal than the product of the norm of S in BG and the norm of T in BH. Okay. Also, if you have involution, we want to jump from the fiber BG to the fiber BG minus 1. And also, we ask that when you're restricting, you are looking for the involution restricted to BG, to the map BG minus 1, that's an antilinear. Okay.
Adam?
We have condition. Say Adam. Adam, sorry, am I pronouncing it correct? Is Adam?
Yeah.
Adam, yes. Yeah.
Okay.
Correct me if I'm wrong. So still those BGs are not Banach algebras, but BE. This fiber
yes,
identity element would be a Banach algebra, yes?
Yes, because we can multiply elements of the same fiber, but they will go to other fiber, right? So if we have S in BG, sorry, let me just write it here, ST in the same fiber BG. The product ST goes to BG squared. That's not necessarily the same fiber. Okay, but in the identity fiber, we will have an algebra, right? If it's in BE, elements in BE, multiplying elements in BE, they will result in the. And we'll say later that BE is a sister algebra, in fact.
Yeah, exactly. Since you have this condition F6, and also from F3 follows that the star also.
Yeah, from F1 to F6, you can prove that it's a sister.
Okay.
Because of the product is restricted there, we will be a Banach algebra and then a sister. Yeah. So we have also this ST star is equal to T star star for all ST in B. Again, let me just mention that to get used to things, where lives, if you have S, again, in BG, and T in BH, ST star, ST lives in BGH, and the star lives in the opposite element. So ST star lives in BGH minus 1. That's BH H minus 1, G minus 1. Okay. Where in these guys, this product lives here as well, because this one lives in BG minus 1 and this one in BH minus 1. Then we multiply, they live in the same fiber, and then we ask them to be equal. Okay. If you involute an element and evolute it again, you come back to the first element, S star S. So it's not only an evolution here, it's an evolution in the total space, this map star. And here something that resembles to the C star condition, but again, this norm is taking, the norms are taking place, are in different fibers. This norm is in the fiber BG, whereas this one is the fiber BE, right? Because this lives in BG, this in BG minus 1, the product in BE, the unit fiber. So this condition, these norms are different. That's interesting. How these conditions work with different norms in different places. Okay, and also we have this. We asked for some positivity condition here, that whenever you have S star times S, it's positive in BE. And why can we talk about positivity in BE? Because with these six first conditions here, we can show that BE is a C-star algebra. Because the multiplication is the BE times BE lives in BE, and the evolution same thing, and then we have a C-star algebra using these conditions.
Sorry, it was a quick question. So from this last condition, it follows that this S star S could be expressed as T star T with T belonging to BE. Am I right?
Exactly. S star S is equal to T star T. And these guys here live in the unit fiber. Yes, exactly.
Thank you.
Okay. So one extra condition that we define is what is a saturated Feldbach. Okay. Here we multiply BG and BH and we get to BGH. And when this taking the span is dense in BGH, it could not be the whole BGH. Okay. But if it's dense, if its span is dense in BGH, then we call for every pair of GH in G, then we call this Feld bundle saturated. Okay. Here are the things that I have mentioned before. The conditions 1 to 6 imply that the unit fiber is of the Feld bundle is C star alpha. And that condition on the order here relates to the order in the C star when it goes to balance. Okay. Another interesting thing is that whenever you have a Feld bundle, each fiber of the Feld bundle is a Morita equivalence B module. BE module, B module concerning to the unit fiber C star alpha, right? And that's the structure. So the left inner product is given by this one. If you multiply ST, note that these guys both right now are in BG. When you go and then if you multiply S by T star, you're going to get to BE, because this one goes to BG minus 1, and then you multiply and goes to BE, and the same thing happens here. Okay. And since it's saturated, oh no, sorry. It's not a Morita equivalence B module, almost Morita equivalence B module. If the module is saturated, the Feld bundle is saturated, then you have a Morita equivalence B module, because these guys will be dense in the unit C star, in the unit fiber. Yeah, that's what's written here. So you have inner products for every fiber has left and right inner products going to the unit fiber. Also, the unit fiber acts on the right and on the left by multiplication on BG, right? Because BE times BE BG lives in BG. So you can understand the multiplication of the Feld bundle as restricted to this setting here as a right and a left action. Okay. So it's a B module, and if it's saturated, then these products here will generate the whole algebra BE. And another interesting fact, and a very, very important fact, is that if now we have a Feld bundle, we have the fibers. The fiber, if it's saturated, the fiber are Morita equivalence B modules, and then you can also prove the following: that the tensor product of B modules, okay, BG, B over BE, the unit fiber B, BH, is isomorphic to BGH via the following method. You take a basic tensor ST, as tensor T, and multiply ST. This map is a Morita equivalence B modules. Morita equivalence of B modules, sorry. One thing to notice is that if the Feld bundle is not saturated, this map here can doesn't need to be adjointable. Okay, even adjointable. It's a B module operator, but doesn't need to be a adjointable operator. Okay, but if it's saturated, it's a unitary operator because it's an equivalence, right? By equivalence between B modules, I mean a unitary map. Okay. So as examples, you have the trivial file bundle. If you have locally compact space, later G will be a locally compact group, but let's stay with a space so far. And you have a C-star algebra. Then, if you consider the trivial Banach bundle over G, where the fibers are B, then you can equip it with multiplication and evolution, like coming from the structure of the algebra. So whenever you have an element G1, B1 and an element G2, B2, they live in different fibers, then you go to the fiber product, and then you multiply the elements of them. Okay, and the evolution change of fibers and evolve the elements. Okay? So that's what we call the trivial cell bond. Okay? Another interesting example: if you have a locally compact group, G and H, locally compact group, and you have a principal T bundle, okay, so a bundle with a right action of T on H, okay. Then you have the quotient space. You define B to be the quotient space of some left action here of T acting on H times C, okay, and the action is given by this. You take an element of the circle, multiply H, Z, and get in each core. You take this guy multiplying H, and T multiplies the second coordinate. Okay, you have this, and this gives rise to a file bundle, where the projection of a class will be come from the projection map here in the beginning of the bundle. Okay. Okay, if you have this, you can also endow it with multiplication of classes, in which you multiply coordinate by coordinate, and the evolution is the same as the previous slide. You change a fiber and evolve the element. Here is this Z is that's conjugation, right? Conjugation of complex sum. So one thing to notice is that this fiber bundle, each fiber is isomorphic to C, to complex numbers, and that they are called fell line bundles. Now, if you have another example, if you have a cocycle with values and values in Z2, but a cocycle going from CT, continuous function of the circle, to Z2, defined in this way, you take like a pair M1, N1, M2, N2, and calculate in T in an element of the circle, and you calculate the exponential. Okay. Assume you have this cocycle here. Then you can define a fell bundle over Z2, where each fiber is constant, is the continuous functions in the circle, okay, and the multiplication is kind of twisted by this continuous to cocycle, this CT cocycle. Some important C-star algebras appear like this R C-star algebra, this structure here. Okay. So here we say how to get from fell bundles to C-star algebras. Okay, if you have a locally compact group, you have a Haar measure on this group. It exists, right? And you have the modular function, and you have a fell bundle, BG pi. Okay. So you consider if you have this fell bundle here, you can consider the set of continuous sections, right? Compactly supported continuous section of this fell bundle. And then you can turn it into a C-star algebra via this convolution multiplication over here. Okay. The product of two sections calculated in an element of G will be this integral over here. Yes, this is great. And you have also the modular function helping you to create an evolution. With some calculations, you can show that it's a star algebra. And then you can complete it with respect to the following norm. Okay. L1 norm. And then you're going to get this algebra over here, L1GB. And then we define the C-star algebra of the Fell bundle as the enveloping C-star algebra of this of the space of continuous functions related with this L1.
Sorry, can you tell me what happens when G is discrete?
That's the usual convolution algebra, right?
I'm trying to figure out.
G.
Oh, yes. Okay.
Because if it's discrete, this will be the counting measure, and then you have the usual convolution product.
If the fiber is one dimensional.
No. Sorry. The higher measure yes, it will be the counting measure, right?
Yes.
And then since it's compactly supported, we'll be dealing only with finite sums. And then you multiply like the usual convolution.
The remark was about the dimension of the fiber.
Please ask again.
So the convolution algebra is the case when your Banach bundle is of dimension 1. If they're of rank 1. The fiber is dimension 1. Okay.
No, yeah.
Otherwise, it's more complicated.
Yeah, but I think I don't know if that's the answer you want, Piotr, but that will become a sum.
Yes. For the discrete group, it is a sum. But I'm commenting about this being the convolution algebra. It's a generalization of the convolution algebra. It becomes the convolution algebra only if the fiber of this Banach bundle is one dimensional.
Yeah, I understand you. Yeah, it's a generalization. Yeah, because here we have also different fibers, so we are multiplying things in different places. Yeah.
Yes.
But I was thinking in a different direction. If I understand you correctly, this G gives you a grading of your space of your script B, right?
Okay.
And if you have a grading by a discrete group, it means that you have an action of a Pontryagin dual. Okay, if you don't want a quantum group, you let it be discrete abelian. Okay.
Mm-hmm.
So then you would have some G algebra, right? So and I'm trying to figure out how does this algebraic structure relate to this convolution.
Well, I know this simply by the C-star algebra of a Fell bundle over a discrete group is the same. But I don't know. Stefan has something to say.
Yeah.
I mean, I think what you're thinking about is the cross product of the of the C-star. I mean, of the group on the C-star algebra. So this will be the generalization of the group algebra.
No, that's the generalization of cross product.
No, I mean,
algebra, right?
yeah. I mean, it was just what Thomas said, right?
Yes.
So in this, we have a discrete group, and then this is the. I mean, if you have you have the dual group action, and then this construction would give you the cross product.
Yeah.
Okay, thank you.
I have also one more question about this enveloping C-star algebra. So you take this universal norm, yes?
Yeah, but with the representations are has to be contractive concerning this one. That's the thing. Not all representations, but the ones that are contractive concerning this L1 norm here.
Okay.
So universal concerning all the contractive representations with respect to this norm.
My name is Ludwig. Hi. Can I ask a question? A comment on this
Yes,
particular case when we have discrete group, even abelian, let's take. I think it's not even cross product, it's even more because fibers can be different, not just the same, probably, yes. So it's something more than just cross product of group by the algebra. Okay.
Yeah, C-star algebras of Fell bundles over discrete groups are a generalization of cross product because the fibers are different. That's why Fell bundles come up. Oh,
okay,
I thank you. Okay, so one example of the cross section of C-star algebra of the Fell bundle of Fell bundles that we defined in the previous slide. In this example over here, when you have a when you have a two cycle of CT valued two cycle, the C-star algebra of that Fell bundle with multiplication twisted by a cocycle is isomorphic to the group C-star algebra of the upper triangular integer valued 3x3 matrices, or the C-star algebra of three-dimensional Heisenberg group H. Okay. So interesting C-star algebras from the literature appear can be are shown to be C-star algebras of Fell bundle. Okay, another examples of Fell bundles in their C-star algebras appear in this setting of as group C-star algebras can be seen as Fell bundle C-star algebras, quantum SU2, and all of these classes here. Okay. Well, as we mentioned.
Oh, wait a second, but this you wrote yourself that it's not obvious, so I completely have no clue what you mean Fell bundle structure on quantum SU2.
Well, Piotr, let me just that's a fact, but I'm not that into this fact too. Piotr, this slide is particularly for a presentation that Stefan used, and we are recycling. But Stefan, if you have a word to say.
I mean, quantum SU2 simply mean you have quantum SU2 generated by two elements subject to these relations, and there you have natural gauge action by the torus, and this is a free action. I mean, that's what NATÁN said before. I mean, you have an action, and then this gives you a grading by the dual group, and this then will fit into this Fell bundle picture. So this is, I think, what is meant here.
So it is a special case of simply graph C-star algebras.
Yeah, exactly. It's a special case of graph C-star algebras. Yes, absolutely.
Okay, thank you.
So whenever you have a graded C-star algebra, you have a Fell bundle over its grading group, right? Because if we have closed subspaces, there are Banach subspaces, and then let's remember that we have AG, G a discrete group, AG, right? And the direct sum of AG, A is a C-star algebra, and you have this, right? Was A. If you consider like the disjoint union of every AG over G, G and G, sorry, you're going to have we have a Fell bundle, a discrete Fell bundle, okay? With discrete base. Again, using the example of compact abelian group acting on a C-star algebra, then we have a gradient, and then we have a Fell bundle over the gradient is over the dual, so we have a Fell bundle over the. And the observation here that this setting is also a Fell bundle over discrete abelian groups. and in this case, saturated cell bundles will correspond to free actions of complete abelian group from interferon. Now, let's talk about equivalence of cell bundles. This will be used later, but that's if I asked you guys to define an equivalence for cell bundles, that's what you guys will be right. So that's what you will be right. So what are cell bundles? We have two cell bundles over the same group with the same unit fiber. Okay. So what is to say that they are equivalent? So first of all, there's a homeomorphism between them. This homeomorphism preserves fibers. Here again, it's an equality, but it suffices to ask that containment property. Okay, so it's a homeomorphism from the total spaces, preserving fiber, sending fiber to fiber, fiber X, in such a way that when you restrict this homeomorphism to fibers, you have a linear isometry. Okay. It will be a linear surjective isometry, in fact, not on the, you can show that it's surjective. Also, that is, the fibers are the same Banach space, equivalent Banach space. And also, you ask that in when restricted to the identity fiber, since they have the same fiber, not only isomorphic but the same, we ask that this map to be identity. Okay. And also we ask this homomorphism condition here. So phi g, that's the restriction of the big homeomorphism to the fiber G. Okay, phi g of S will live in B2, the fiber of G in the cell bundle 2. Okay, if assume S belongs to the fiber of G in the first cell bundle, and T belongs to the fiber of H in the first cell bundle, then since this homeomorphism sends fiber to fiber G of S, psi G of S goes to the second fiber of G, the fiber of G in the second cell bundle. Same here with psi T, sorry, goes to BH2. And then when you multiply them, these elements, you're going to get to the fiber BGH of the second cell bundle. Okay. And the same happens if you apply BG psi GH of the product ST. It will live here, and we are asking that these guys to be equal. What you call a homomorphism condition. Okay? And the same for the start. You jump from fiber G to fiber G minus 1, and its respective evolution. Okay? So that's what we call an equivalence between cell bundles B1 and B2. Okay. Yeah, and because of these conditions, of course, every fiber, if you remember, every fiber of a cell bundle is a equivalence B module, and it will be a Morita equivalence B module. This restriction map C. This guy over here.
May I have a question?
Please.
So your demand number 3, the condition number 3 of this psi x being a linear isometry is very strong. What if it's replaced by simply an isomorphism?
Yeah, you don't want isometry, right?
Yes, okay. you need isometry.
Yeah, that
So why the preservation of this norm is so important here?
Because we will have then a Morita equivalence B module.
Yeah.
You have the.
Yeah, but next you have isomorphism of Morita equivalence by modules.
Yeah, but okay, yeah. So I will use this result later to show that certain maps are equivalent, but that's a well-known notion of equivalence between file bundles. So I can go deep in this in why it requires to be an isometry.
Is there a notion of a morphism between file bundles over the same group G?
Yes. And then here you just have a linear map, and it will not be a homeomorphism, but it will require preservation, sending fiber to fiber. Okay, yeah.
So this means that your equivalence is even stronger than an isomorphism of file bundles because of this isometry condition.
No, but no, because we can have bundles without asking them to be Banach, normed spaces. It could be only vector spaces, and then your notion will be fine. But if you are adding an extra structure that is a norm, for me makes sense to ask for more to be an equivalence.
Yes, but you said that if you consider morphism between file bundles, you do not demand this isometry.
But continuity.
Okay. So this means that isomorphism of file bundles is less restrictive than your equivalence. So it's a strange wording because usually equivalence is something more flexible than isomorphism.
No, but
your
for
isomorphism
me,
is more flexible than your equivalence.
No, but for me, when you say about
it was only the linguistic.
Yes. But when I hear someone to say two Banachs are isomorphic, two Banach spaces are isomorphic, I think about isometry, not only linear bijection. Or I don't know if you guys think the same, but isomorphism of Banach space, an isomorphism between Banach spaces is an isometry, right?
Yeah.
So I don't know if you're isometry. Sorry. Yeah. Say please.
A quick question about this fourth condition in this notion of morphisms, general morphism.
Okay.
So how this fourth condition is defined for morphism?
This one?
Continuity.
For condition is that's please say again. I think I have.
Okay, my question is the following. In this notion of equivalence, you have this condition that on the fiber over the unit element, you have strictly identity. And how about what are these?
How about an automorphism or something? Yeah, that's something that appeared in our calculation. We will always require that these maps to be identity, and that's a choice that can be made. So we will require this. Yeah.
Even for the general notion of morphisms, yes.
Okay. Oh, in the general notion of work that I mentioned. Okay. I don't know. I don't know. I have to consult the literature. Yeah. I'm not. So yeah, I don't. I'm not sure if here we are asking this map to be identity. Okay. That I don't know. I have to look.
Stark homomorphism would be the most natural candidate, since over
this
unit element you have a structure of a sister algebra, so this would be maybe the most natural.
Yes. I think you are.
Okay, thank you.
Okay. So guys, now about the topologizing FEL bundles, not only Banach bundles. So imagine again that you have a set B, okay, in a surjection onto a locally compact group. Again, you start thinking that it's only a set, okay? So, but in this setting, you have this only a surjection, and you know that the fibers of these surjections are Banach spaces, okay? And also, you know that there's a multiplication between the fibers and an evolution satisfying all the requirements for B to be a FEL bundle, except the topological requirements. Okay? So this guy has no topology.
I have a problem with this notion of compactly supported. Okay, you explained it on this on the next lines. Yes. No.
Where?
Furthermore, let gamma be a fundamental family of sections, meaning a star of compactly supported. So, meaning what? Since B is only a set.
Okay, section mean yeah, B.
Section is fine.
No, but the sections goes from where to where? The section goes from G to B, right?
It does make a sense.
Okay. Yes.
Because it's a subset of G, which is locally compact.
Yes. Okay. Yes. Okay. Thank you.
Yeah. Okay. And then so B is a set, and then we want to topologize. As FEL proved, we could use sections again. But before, if you want to come up with some topology on B, okay, you need sections. So let's start. So we ask we take a set of we call a set of sections to be a fundamental family if it's a star algebra of compactly supported sections of this map here. But what? So remember that we defined product of sections, right? Remember that we have a multiplication over here, and remember that we defined it. What's the product of two sections? Sorry. Okay. That uses the Haar measure here. So we have product, as Adam noted. We have topology. We can say what is a section. What's compactly support? We can say what is a section with compact support. We have a product, so we can consider a star algebra of these of sections of compactly support. Remember that in this definition, the product of sections, we use the product of the bundle, right? We use here, we use here the product of the section of the elements of the bundle. As H, T, H minus 1, H minus 1, G. So S, H. T minus 1. H minus 1. So we are using everything that we have at our disposal here. We have sections, we have compactly supported sections, we have product, and then we have a star algebra of compactly supported sections. If you ask that,
sorry, I have a question. I have a question.
Tell me.
Okay, if B is only a set,
yes,
then what kind of section do you mean? Because G is a topological space. If B is discrete,
set theoretical section.
Okay. Even discontinuous sections. Okay.
Yes. No, yeah, we don't have topology, but we know what is compact support, right?
Of course.
It vanishes outside of compact. Yeah. Set theoretical.
But what guarantees that after topologizing B, these sections become continuous?
A theorem. A theorem
theorem
guarantees
perfect.
that. Yeah,
Okay.
theorem. Yes.
Okay,
So,
thank you.
So we have this setting, we have this condition, this star algebra here of sections, and assuming that these two conditions are satisfied. So when you apply the all sections to an element, you get an element in a dense subset in the corresponding fiber, okay, for every G. And also, if you have this continuity condition here, then Takeishi proved the following result. Okay. Under the above hypothesis, there exists a unique topology on B. Remember that it has a multiplication, it has an evolution, it only doesn't have topology. So that's a unique topology that makes this mapping to a Fell bundle. And all sections in gamma are continuous. Okay. Mm-hmm. So that's the way we topologize Fell bundles.
Sorry, I have a question.
Please.
Quite general. In fact, do you view these theorems about uniqueness of this topology as a somehow generalization of the situation from C-star algebras, where the norm is also unique? Since this is very remarkable that you have a unique topology. It's a very strong condition.
Yeah, I understand your question. We know that with there's only one norm. It comes from the spectral radius and C-star algebras. Yeah. I haven't gone deep in these proofs, but this proof is in the paper of Takeishi and the Fells. Also, let me just mention that this condition that's a star algebra is used to prove that the multiplication is continuous. Okay, if remember that if we had only a vector space, it will be a Banach bundle. It uses the Fell's result. So, but I haven't gone deep into Fell's proof to
but
see
even
what's
in
happening
the case of these Banach bundles, you have also this uniqueness, yes?
Yes, we have. Yeah, we have this uniqueness. Yeah. So the question is why, right?
Yeah.
But I don't know. Just to mention that you can choose another set of sections and have another topology, right? It's unique concerning to the sections you chose. Okay. We can have different topologies.
Okay. So let me be more precise. So in this lemma, the uniqueness is with respect to making the structure of a
choice of gamma
and sections being continuous, or second option, uniqueness is only with respect to making this be a Fell bundle, and then additionally all sections are continuous. This is not the same. You see my point?
Please repeat. I talked while we were speaking.
So first option, there exists a unique topology such that, and now two conditions, that this pi is a Fell bundle. Second condition, all sections are continuous. This is a first option. Second option, there is a unique topology that makes this pi a Fell bundle, and additionally all sections are continuous. You see,
I think the second option.
Okay. So, but if it is a second option, then it is not.
No. It was first option.
It was
your first reading was right, I suppose.
Yeah, probably.
So it is not about uniqueness topology. It is about, in a sense of uniqueness of a completion, depending on the choice of this fundamental family of sections.
Okay, so probably the same goes for these Banach bundles, and then this explains this strange phenomenon that you have uniqueness. Okay, you have uniqueness, but provided you specify your favorite
family. Yes. Different families generate different topologies.
Okay, so I withdraw my suspicion that this is somehow analog situation to a C-star algebra. Okay.
To C-star, yeah.
You also have to specify your sections. Okay, thank you.
Yes.
But
Stefan, you have a comment?
Adam, may I comment your comment, Adam? Okay, so
Sure.
but you were very close to what should be said, because this family of compactly supported sections defines a dense star algebra. So what is, if you think about this felt bundle as an analog of the sister algebra, it's a uniqueness of the completion. Of this dense star subalgebra to a sister algebra.
This gamma, this fixed gamma here, will become a dense star algebra in the sections when you complete. Okay.
Yeah.
Okay, thank you. Nice.
So, Stefan, you were with the. You want to comment something? I don't know. Oh, you withdraw your. So we know. Now let's go to classification. But what we have so far is that whenever you have a family of Banach spaces, VG over, let's say, a discrete group or a topological group, the union can be topologized using sections. Okay, but we will not use this in the following things, because we will consider the discrete case first. Okay? So to continue, I have to mention what is the Picard group of unital sister algebra. Okay? So fix a unital sister algebra B. The Picard group of this sister algebra is the group of set of equivalence. Is the group of equivalent classes of Morita equivalence B modules of this sister algebra. So let me just write here: Picard group of B is the class of Morita equivalence B modules. Equivalence classes, no? And Morita equivalence. Remember that equivalence of B modules refers to unitary operators. Okay? So we have this sister algebra. So this group here. So what's the product of the group is the tensor product. Whenever you have n, m times n means taking the tensor product, internal tensor product. And some examples.
May I have a question?
Yes, please.
There is another definition of a Picard group, which is simply the group completion of this monoid of invertible Hilbert B bimodules. Is it the same?
I think so. I don't know what you mean by invertible Hilbert B bimodules, but I think it's the same thing.
It's the same thing. Okay.
Well, invertible means simply that you have another bimodule which you can take the tensor product with, and you go back to the
it gives you beat.
Yeah. Okay. So I think it's the same. That's the growth.
Okay, so this Morita property is equivalent to invertibility of these B bimodules, probably. Okay.
Yeah.
Okay.
I'm not sure, Thomas, but if it has the same name, it may be probably the same group. So that's a group.
How computable is this Picard group? If I throw at you a sister algebra, will you give me the Picard group?
So I have some examples, but I'm not sure if in general they are very easy to compute.
Okay.
Not sure. So, for example, here, if you have a finite dimensional sister algebra, its Picard group is isomorphic to the permutations of its spectrum. Okay. In the case you have a commutative system, unital commutative sister algebra here, it's isomorphic. X is compact, so the Picard group of C of X is isomorphic to the same direct product of the homeomorphisms of X with pic X. That's Picard group of the space. That means the group of equivalence classes of complex line bundles over X. Okay. And also, if you have the quantum...
Sorry, may I comment on this?
Yes.
So this means that what I said about the different definition of a Picard group, your second example shows that these are different things. Because my definition of the Picard group would give this Picard group of the space X in the context of the second example.
Wow.
And now it's twisted by homeomorphism of X.
Pic X is equal to pic.
Yeah.
Sorry. You're saying that it's the same group?
Yeah. No, it's not the same.
No. What? So in your definition, what's the Picard group?
It's twisted by homeomorphism. It's a cross product.
No. But in your definition,
in my definition, it was pic of X. But in your definition, is twisted by homeomorphisms.
Yes.
Yeah. So this is the difference.
Okay.
Now it's clear.
I didn't know this notion.
Sorry, NATÁ, what exactly do you have in mind by saying the spectrum of a finite dimensional sister algebra?
It's characters. It's irreducible representations, right? It will be finite, I think. No.
Okay, okay, here I just have a finite direct sum of full matrix algebras. So you mean the sort of counting these blocks of full matrix algebras will be your spectrum, right? Labeling this.
I think so, yeah.
Okay.
Yeah, so for matrices, it's the one point, yes?
Exactly, yes.
So another example would be the quantum two torus or the rotational algebra of irrational rotation. Let's say that's how I know this algebra here. So the Picard group of the quantum two torus is the outer automorphism of its outer automorphism. If theta is a quadratic number, okay, everyone knows what is a quadratic number. It's of the form a, b, square root of c for a and b rational, and c an integer, positive integer. Okay, so if it's quadratic, is the outer automorphisms, and if it's not quadratic, it has here a semi-direct product by z. Okay. So I don't know if that's computable. It's easy. It's apparent if it appears to be computable for you, Piotr.
Yeah, I mean, so for instance, it's a very nice class, finite dimensional sister algebras. Fine, that's very computable. Then you have a classical case, which somehow we have a discrepancy between the classical concept of a Picard group and this sister algebraic. And I'm not sure I understand how we got this. So that's the result. I understand for theta not being 1 or 0. But what if I insist on theta being 0? What if I just want to have a commutative torus? Then I come back to the previous class, right?
Yes.
Exactly. But now I'll have cross product instead of but so what does it mean outer automorphisms then?
It's a quotient of automorphism by inner automorphisms.
Is it automorphism by the inner automorphism, right?
But when you are commutative, there are no inner automorphisms. So okay,
so you don't have inner.
Okay. Okay, thanks. By the way, NATÁ, you have -4 minutes left.
Oh my gosh. So here is where the talk starts.
Well, here's where the talk
-4.
ends.
No, okay. So let me just recall some. Let me try to be quick here and explain the problem, because it's very, very interesting, and then I can just show the results. So
okay.
Well, we saw so far that we studied file bundles. I showed the file bundles, and an interesting invariant for file bundles is what I call a Picard homomorphism from the base group to the Picard group of the unit fiber system. How it's done. So the thing is, whenever you have a file bundle, this map that sends G, remember that every fiber was a Morita equivalence B module, right? And so if you take this map that sends an element of G to the Picard group of the unit C-star algebra of the file bundle, this gives rise to also the important thing here: the file bundle is saturated. Okay? Whenever you have it, that gives rise to a homomorphism, and it's very easy to show that it's a homomorphism because of the following calculations. You have G of H being sent to the class of BGH, but because if it's saturated, we know that this guy is the tensor, BGH, and then is, as you can imagine, BG times BH, the product in the Picard group. So that's a homomorph. So what we have here, we have the following: file bundle B, a file bundle gives rise to a homomorphism in the Picard group from G to the Picard group of the unit of C-star. And now the question is the following. Let's see the other way around. If we start with G, a group, B, a C-star algebra, unital, okay, and suppose you have an homomorphism, I'll denote psi, from G to the Picard group of this unital C-star algebra B. The question is the following: there exists, or how many? Question is the following: there exists a file bundle B, file bundle over G with unit fiber B, such that when you compute this Picard homomorphism phi B, gives this previously fixed psi. That's the question that we answered in the paper and we classified. The thing is, there's not only one, okay, and it depends on some cohomology theory of G in the unitary, in the center of the unitary, the central unitaries of P. Okay, so these guys, when there exists, they are classified by this cohomology group here. It's a shame that was the part that I have prepared most in the talk, and you said that it should be 90 minutes. I didn't have the time, so but. I could talk another time if you want, Piotr. But
surely, yes. Next semester,
it will be a pleasure to. Yeah, it will be a pleasure to start from this point to show what we have done. Okay, But yes,
today I gave
think
a full 2-hour talk, so I understand your pain. Today my talk was full 2 hours. Even more.
Okay.
Yeah.
Okay. So that's the main question that we answered in the paper, and I think it's a very interesting question. And it's nice to see how the second cohomology group appears there, and how a cohomology theory comes up there. Comes up there. So yeah. So thank you, and I'm sorry for not
Thank
even
you so much. Thank you.
getting that.
Thank you.
Any further questions from anybody?
So maybe a quick one. Sorry, I don't know how to raise my hand.
That's okay.
So I have just a very quick question. At the beginning, you gave the definition of G-graded, where you assume that each subspace is closed. But because I remember the definition of strong grading, where they don't have this assumption. I don't know if it is a different definition or maybe it's equivalent. Maybe in some, like for the integers, is always closed.
Yeah, that's a good question. I was thinking exactly the same.
Is stronger grading of sister algebras?
Yeah, it means that you simply have equality, not that it's dense.
Okay. Okay, but it doesn't require these guys to be closed, but you have equality here.
Yeah, so I don't know if it is automatic that is closed, or maybe we don't care about this assumption in that case.
No.
Maybe it's different.
No, the thing is, whenever you have you can close your subspaces, right? So you have a grading, but I'm not sure if it's equivalent.
Okay.
I'm not sure. I don't know if it's equivalent.
Yeah, you are right.
Because also the strong grading in the other sense, where you don't assume that things are closed, is equivalent to having like a principal action of U1 in the in the Elwood sense. So I don't know if this gives something more than principal action, or I don't know.
But the strong, just to mention that this notion of grading is for discrete things. Your stronger gradings are for discrete groups or discrete structures, or you have some topology.
It's algebraic. It's completely
algebraic.
It's
algebraic. It's algebraic.
Grading, algebraic. Strong grading simply means that you have the
equality
condition for the coaction of a group ring of algebra. Okay. So you coact with a group ring algebra, and you demand that this coaction be Galois, and this is exactly strong grading.
Well, I'm not aware if these notions are the same.
But it should be. I believe the saturation and thinness are the same.
Yes,
I believe. But I'm too sleepy to think about it.
Okay. So thank you very much. Anyways, it was very nice.
Thank you.
Okay. You will put the complete slides online, even what?
Yes. Yeah, exactly. So,
yes.
please, Nata, remember that's very important. Please
yes,
correct
the
slides because you have the wrong date. Correct the slides and send me as soon as possible. Yeah.
Yes. I'll do that.
Okay. I have a question about a possible extension of this theory to quantum groups.
Yeah, again, reading my thoughts. Yes.
Where are the problems?
I don't know if I can answer. I don't know if I can answer this question because I'm not. I have to say I'm not that familiar with quantum groups, but that's what
Thomas,
was.
Can you?
Please.
No. I'm just wondering, Thomas, what you mean by quantum groups here. I mean that the group on the base group is a quantum group.
If the base is a quantum group.
Yeah.
Okay. I thought it was
even discrete to begin with.
I mean, Thomas, that's. I mean, I think we write that in our paper that that's something that one can do as a future direction. Absolutely. But I mean, there are some technical difficulties. Then, of course, what is a Picard group? how do you do? But I mean, let me just say this. There is a similar theorem for topologizing Fell
Like
bundles
with Fell lemma?
over quantum groups. So that tells you once you choose the sections, then you get a topologizing thing. So something.
So do you mean like quantum group version of this Fell lemma, right?
Yes, exactly.
Okay.
Huh?
Very happy. Yeah.
So could you, NATÁ, could you come back to this lemma?
Yes, of course. This one?
To have it in front of our eyes. Yes. Okay. Topology. So now this script B should be some sister algebra, dually to this problem. I don't know what even.
Okay.
So I have a problem in understanding this extension, because then it would require this bundle would require to possess a total quantum space with fibers being Banach spaces.
Yeah, there's a problem what you mean by fibers then, indeed.
So, sorry if I may interrupt again. That what I said was wrong. I thought about groupoids, of course. So groupoids you can generalize. Yeah, then you don't have this problem. But generally speaking, if I'm not completely wrong now, so I mean gradings corresponds to coactions of the group ring, right? That's
this is exactly what I said. Yes.
Exactly, that's what Piotr said. So and of course these Fell bundles, they're heavily related. Also, I mean, you can define what coactions by quantum groups are. And in this sense, you can say what freeness or saturation or strong grading is. But I mean, it's dual to this. I mean, it's you can say what a strong or a saturated or free coaction on a C-star algebra is, and this is then related to this Fell bundle picture. But I mean, not sure if this is what you have in mind here. But this is maybe the way to generalize this to quantum groups.
Yeah, surely that's kind of clear. But the issue is, what is a fiber? How do you say that your fiber is a Banach space if you have no points over which you can take a fiber?
I mean, here the picture would probably be something. I mean, let's say you have a compact quantum group. Then, I mean, of course, you don't have fibers anymore, but then you get a decomposition into isotypic components over the irreducible representations of the quantum group.
Okay. Yeah, I like the idea. Yes.
But something along these lines.
Yeah, I fully agree with you. Okay. Okay. All right. Any further questions? I don't see any raised hands. So in this case, muito obrigado. Muito obrigado, NATÁ.
Thank you, and I'm sorry.
Let me stop recording.